The question is number of operations to make a network connected. You have to return the minimum number of times you need to do this in order to make all the computers connected. If it's not possible, return -1. You can read the description as well. We are going to use the union find algorithm. Now, if length of the connections is less than n-1, you return -1. So a connected graph on n nodes needs a minimum of n-1 edges. So moving cables will never change how many you have. So you can just have an early exit and return -1 as suggested over here. Then parent is equal to list of range of n, and rank is 0 times n. Now parent of x is the node x, points to its groups tree. Initially, every node points to itself, meaning n separate single node groups. Rank of x is a rough upper bound on that tree's height. It is used only to decide which tree gets hung under the other when you are merging. Now find. This is again the classic union find algorithm. So in this find function, you basically check which group does X belong to. So over here, we keep walking until you hit a node that is its own parent. So the self-pointing node is the root, and the root is the group's identity. Two nodes are in the same group exactly when they have the same root. This is path compression. So before stepping up, repoint X at its grandparent, halving the distance to the root. It doesn't change which root you reach, it just flattens the tree so future finds on this path are faster. Then this is actually taking the step forward, and then you return the root. Then this is our union function. So you are merging two groups, report whether anything changed. So this part, it gets both roots. If they match, A and B were already connected, this cable is then redundant. And nothing to merge, so you just return false. Then this part is your union by rank. So you swap, so RA is the taller tree, then hang the shorter tree's root under it. Attaching the shorter under taller keeps the combined tree from getting deep, which keeps find fast. Then, in this condition, height will grow. So the condition is that if RA was already taller, if the height of RA is equal to height of RB, then yes, your height will grow and you are stacking two trees of equal rank. And at the end, the merge happened, you return true. Then this is our main loop. So in this, we start with n isolated components. Each successful merge turns two components into one. So we will do a decrement over here. The redundant edges just return false and we leave the count alone. And at the end, we are returning components -1. So k components need k -1 links to become 1. So if, for example, if over here there are 4 components, so it needs 3 links, right? And you just return components -1.